All right, this one's a little long. It's just homomorphism theorems, but I mean, there's a lot of details, sort of. So I think the two directions are different enough that we're going to do them differently. Um, but there might be some way to like reduce. I don't know, whatever. So let M be an irreducible left R module. So here I'm saying okay, so the thing I say here is let I be a left ideal. That's a dumb idea because I don't use that ideal. I use a different ideal. So in this direction, we actually here. Let's just start doing it. Since M is non-zero because it's irreducible, we can fix some M in M mod 0. And the main issue in this is if we want to use the homomorphism theorems, then we need a homomorphism. So where do we get them? So in this direction, we use this non-zero element to get our homomorphism. Consider the map phi from R to M defined by phi of R is equal to Rm. And what we're going to do here is we have to keep it. So M is a left R module. And so here, this R that we're looking at, we're not just looking at R, but we're going to be considering, or I'm pretty sure we're going to be considering R as a left R module. And that's going to be pretty important. So anyways, we're going to define it like this. And since M and R are non-zero, why is M non-zero? Or why is R non-zero? Well, would this question even make sense if R was 0? I don't think the question would even make sense if R were 0, because then it couldn't possibly have a maximal ideal, because the only ideals would be the 0 ideal. So we're not even going to think about that. So since these two things are non-zero, the image of phi is non-zero. So now this image of phi is not okay. We're going to use this. So also, what else do we know? Image of phi is a submodule of M. That is using one of the homomorphism theorems, and we can use that because like we actually get a submodule because we're considering R as an R module and M as an R module. And so there we go. So image of phi is a submodule because image of phi is obviously closed under the action by R because because M is, so phi goes into R. So the image of phi, so if you take something in this image and you act on it by R, are you going to stay? Is this actually a submodule? It should be by the homomorph. Yeah, of course, that's the whole point of the homomorphism theorems, is to prove that this is a submodule, because we have a link between the between the submodules of the two. And of course, R is a module, and so it relates to a R is a submodule of R, and so it relates to a its image is a submodule of M. So anyways, so this is a submodule of M, since M is, let's see here, since M is irreducible, image of phi is either equal to 0. Well, yeah, it's either equal to 0 or equal to M. Image of phi contains the element M, right? Because you just R must contain 1. We're not considering rings here, which are rings of the identity, which is a hilarious definition. But so R has the element 1, so phi of 1 is just M, and M is non-zero. So image phi is not 0. So the image of phi is M. By the homomorphism theorems, one of them, whichever one, R mod kernel of phi is isomorphic to M. Okay. Let's see here. So now this kernel of phi is, let's see here, we want to show that M is isomorphic to R mod I, where I is some maximal ideal of R. And so kernel of phi is going to be the ideal that we want to prove is maximal. I now claim ker phi is a maximal ideal of R. And of course, obviously it's an ideal because kernels are ideals. Let's see here. We have a 1-to-1 correspondence. Maybe the P belongs on the other line, whatever. I don't know how those hyphens work. Leave that to Microsoft Word or LaTeX or whatever. 1-to-1 correspondence between the submodules of of M and those of R containing kernel of phi. See here. So then, since M is irreducible, this is strange. We're using irreducibility twice. It's possible we could have wrapped this up a little more neatly and not had to use this twice and just used it once in one fell swoop, but whatever, this is what I got, so it'll work. So, since M is irreducible, any submodule or the modules of M are 0 and M. Then look, these correspond to the submodules kernel of phi and R of R. Because if we look at our map, phi sends r to m, and it sends 0 to 0, so that's the correspondence between the submodules. So R contains no submodules between kernel of phi and R. Okay. But the submodules of R as an R module, well, yeah, that's what I mean by the submodules of R, because R is the abelian group, and we're calling it a submodule, meaning that it's got the R module structure. Anyways, the submodules of R are the ideals of R, and so there are no ideals between kernel of phi and R. So hence kernel of phi is a maximal ideal. And so there we go, that completes this direction. So we're done with half of the exercise. Hooray! So for the other direction, suppose M is isomorphic to R mod I as R modules. So R mod I here is a left R module. For some maximal left ideal I of R. Let phi from R to R mod I be the natural homomorphism. Turns out natural here has a very specific meaning when you get to category theory, but I don't know what that is, and you don't need to know it because it's obvious. It's the obvious map. You send R to R plus I. There you go. It's natural. But anyways, so we have, by the homomorphism theorems, a one-to-one correspond. Wow, I did this even differently again. Between the ideals of R mod I and the ideals of R containing I. And since I is maximal, the ideals of R mod I are 0 and R mod I. So now let N be a submodule of M. Then let's see here. N so then N because of our course here I'll be more explicit here. Then N is or corresponds. So we know that M is isomorphic to R mod I. So under this isomorphism between M and R mod I, N as a submodule of M corresponds to a to an additive to a submodule of R mod I, i.e. an additive subgroup of R mod I under the addition structure, which is closed under the R mod structure, but closed under multiplication by R, i.e. under the R module structure on R mod I. But then this means, again, that n it corresponds. Keep wanting to say that n is isomorphic to, but it's not. Well, I guess if you were to restrict it, yeah, I guess that would be a good way to say it, because if you have an isomorphism and then you have a submodule, then that's gonna map to, yeah, it's image, obviously, yeah. Then n is isomorphic. I wasn't sure if that was just me being rigorous. Like when I wrote this down, I wasn't sure if that was me being rigorous or me being more intuitive. I guess saying that something corresponds to, that's a little more intuitive, but saying isomorphic to, that's more rigorous. So n is isomorphic to an ideal in R mod I, because that's exactly what an ideal is. Because if it's closed under multiplication by R, then it's closed under multiplication by... Right. Okay, so maybe this isn't... There's a little bit of a nuance between this relation between R acting on n and R mod n acting on n, but it really ends up being the same thing because of how we define multiplication in R mod n. But yeah, whatever. I'm just going to keep this isomorphic here. It might be a little ambiguous, or I might be being hand wavy here, but it works. So it means that n is isomorphic to an ideal in R mod I. So n is isomorphic to the 0 ideal, or n is isomorphic to R mod I. So what does that mean in terms of n's relation to m? So n equals 0 or n equals m. And then hence, m is irreducible. Okay, so there we go. There's a lot of details going on here because all these things, like we have R is a ring, but it's also an additive group, but it's also an R module, and R mod I is an R module, but it's also an R mod I mod. No, it's not an R. Well, we don't think of it as an R mod I. There's a lot of details going on here, but the structure, all the structure that you need is here, so you don't have to worry about it so much. And so that's how you go about this proof. And so here you go. We're done.